Welcome back. We are today at lecture 26, Math 141. We are in the middle of chapter 3, section 6 in our textbook, and that topic is implicit differentiation. So we have looked at implicit, which is not a whole lot different from the chain rule. Yesterday, real quickly at the end of class, I think we hopefully did justice to it, the derivatives of inverse trig. And you might want to make a mark in your notes. Really what you need from inverse trig is you need to be able to derive inverse sine. And then eventually in this course, in this sequence, you're going to have to do the antiderivative. So when you see an integrand that looks like the derivative of inverse sine, you'll be able to work your way back to inverse sine and inverse tangent. Now, I think we did inverse cosine. It happens to be just a SIGN sign change from inverse sine. So frame and put a star beside inverse sine, and the same with inverse tangent. You probably won't actually use inverse cosine all that often. All right, orthogonal trajectories finishes us in 3.6. You've probably seen or heard the word orthogonal in a math or math-related course before. If not, then that'll be a new vocabulary term for you today. Orthogonal. If things are orthogonal in math, what is that? I guess it'll be a new thing for you today. It means that where they meet at right angles. If things are orthogonal, they are perpendicular. So we've got some paths or curves in the plane, and where they actually make contact, they're going to form a right angle. But it's not the curves themselves, it's the tangent lines. So the tangent lines are perpendicular at the point or points of contact. So in essence, it's curves that are perpendicular by the fact that the tangent lines to the curves at that point of contact are perpendicular. And hopefully the curves will look like they are kind of perpendicular, but it's really the tangent lines. Now we will, in this course later, be able to start with a family of curves and find another family of curves that are mutually such that they are mutually perpendicular. We will be able to find the orthogonal trajectories. That's not what this is. Today is a validation. If we're given two sets of curves, can we prove that they are these things, orthogonal trajectories? So we will revisit this, and this is just a very kind of brief encounter. Now, when I said family of curves, there's going to be some C's and K's in the curves in different places where there typically is a number. So if this were x equals 8y squared, or x equals negative 16y squared, or x equals 1y squared, what are these? The x is first degree, the y is second degree. These are parabolas. Okay. Now, normally you see y equals x squared, right? This is the other type of parabola where x is equal to y squared. So these are the parabolas that are not functions. So these are the kind of the open right or open left parabolas. So this is a family of parabolas. We'll make a sketch when we're a little further along in this problem. The set of points in the plane that are, hopefully we're going to be able to prove that they're orthogonal trajectories. Is this set. What does it sound like to you How are we going to be able to do this? How are we going to be able to prove that where they meet, they are mutually orthogonal? Chandler?
Their slopes are inverses of each other?
Keep going. Not inverses. That's part of it. Negative.
Negative
inverse.
reciprocal.
Okay.
Yeah,
So
okay.
we'll take their slopes. What are the slopes? Derivatives, right? And we'll validate that the slopes are, in fact, negative reciprocals of each other. That's how we're going to do this. What is this family of curves? Just put a number in there. Let's say it's 1 for C. These are not circles, but close. These are ellipses, right? Now, if the x squared is really technically over 1, right? X squared is really x squared over 1. So if the C were 1, this would be kind of a pretty common ellipse. So we've got this group of parabolas and this group of ellipses that apparently, if you would plot them in the plane for different values of k and c, you would see that where they meet, they actually kind of form right angles. So let's check this by finding from the parabolas, we want to find dy over dx, and for the ellipses. So am I safe to assume this is everybody in this class? This is your first encounter with orthogonal trajectories. Is that correct? Okay. And for the ellipses, we want to find dy over dx. And then see if we can actually validate, in fact, that they are mutually perpendicular. All right, x equals k y squared. We want to find dy over dx. So this I think now is hopefully apparent why it's in this part of the textbook. Let's differentiate. What's the next word I'm going to say? How do we differentiate this? Implicitly, okay? Why it's in this part of the book. Let's take this equation and differentiate implicitly. What's the derivative of the left side? 1. K is a number, so it is like a coefficient. It comes along for the ride. What's the derivative of y squared with respect to x?
2y dy dx.
So if we solve that for dy over dx, (1 over 2ky). Is that correct? Now the k probably we're going to have to deal with. We're going to have to get rid of that k because we're not going to have a k in the other one. There isn't a k to begin with. So if we were to eliminate k, if we need to, from the original equation, what is k equal to? Good. X over y squared. So we'll keep that in mind if we need to use that, which we probably will. We'll throw that in there for k. All right, the other equation, it was y squared over 2, so I'm going to call that 1/2 y squared. So let's differentiate implicitly. Yes, Ken?
K is just a constant, right?
Yeah.
Same as C?
But it's a constant that's tying these two variables together somehow in this situation. That is part of the interrelationship of x and y up here. K is. But it is just a number. But when we come back to actually validating that this derivative is the negative reciprocal of this one, that k is probably going to get in the way. So what is k on this problem? We need to replace it with that, possibly. More than likely, we're going to have to. But you're right, it is just a number. But it's a number that interrelates the x and y things on this family of parabolas. What's the derivative of x squared with respect to x?
2x.
2x. The half comes along for the ride. What's the derivative of y squared with respect to x?
2y dy dx.
Okay. I have a pretty strong feeling that you guys are going to do well on this part of the test, because when I say what's the derivative of y squared, I'm not having to pull this part of it out of you. You're readily giving that, and that is the primary problem that I see, especially when you first start doing implicit differentiation. So I think you have that, which is good. That bodes well for you getting quality answers in this particular section. Derivative of the right side is 0. So we're not going to have a C here, and we're stuck with a K up here we're probably going to have to replace. So half of 2, those are gone. So y, dy over dx is what? Negative 2x? So dy over dx is?
Negative 2x over.
Negative 2x over y. All right. So we want to kind of compare and contrast this derivative with this derivative. Are they negative reciprocals of each other? Not yet, they're not.
Not
So let's
yet.
get rid of k. So for k, we're going to replace it with what k is equal to on this original equation. So we've got in the denominator a y over a y squared, which is knocks one of the y's out down here in the denominator of the denominator, right? So we've got a 2x over y. And what's 1 over the fraction 2x over y?
Y over 2x.
Y over 2x. So did we prove what we set out to do?
Yes.
Yes. This derivative up here, let me extend this. This derivative up here for the parabolas, dy over dx ends up being y over 2x, and for the ellipses, derivative is negative 2x over y. So they are negative reciprocals. Therefore, they are orthogonal trajectories. Where they meet at that point of contact or several points of contact, they are in fact perpendicular. Everybody see that? That and that are negative reciprocals. Let's make some sketches and see if these are probably going to be rough. But parabolas. The parabola equation or the family of parabolas look like that. What if that k were 1? What would that look like? Open to the right? What if that k were 8 or 1/12? What does that do? That's how fat or how skinny they are, but they still open to the right. Is that correct? So we could have one that is real fat, one that is in here. What if k were negative? Okay, we can take every one of these and just flip it over the y-axis, right? Take the mirror image over here. And again, you can change coefficients to determine how skinny or how fat. But these are the parabolas that are non-functions because the x is first degree, the y is second degree. All right, the other set of curves. X squared plus y squared over 2 equals c. What if c were 1? Where's the major axis? If c is just the kind of the simple version, if c were 1. Major axis on the x-axis or on the y-axis? Okay. Isn't the larger denominator under the y squared term? If c were 1, this would be x squared over 1, y squared over 2. So isn't this the larger denominator? So the major axis would be either on or parallel to
Y.
the y-axis. So in this case, on the y-axis. So they're going to look like this, or this, or this. So we've got a family of parabolas that either open right or left. They're either fat or skinny, depending on the value of k, depending on the value of c. We've got this family of ellipses whose have their major axis on the y-axis. Now, I don't know how good my diagram is, but if it were accurate, this is what we should be able to do. Here's a point of contact. Here's the tangent line to the parabola. Here's the tangent line to the ellipse. What should be the case with those two tangent lines? They should be perpendicular, and you should be able to check that virtually everywhere. Here's a tangent line. Here's a tangent line. They should be mutually perpendicular. And we know, in fact, if this were more accurate, it would be true because we've already done the algebra in the background. But hopefully it kind of looks that way on the diagram as well. So those are orthogonal trajectories, at least to start with those. You will revisit those in, that's in Calc 2, I believe, where you actually start with a family of curves and then you find the orthogonal trajectories. I said you would have an opportunity to ask WebAssign questions, but I lied, so we're not going to do that. Yes, we are. We're going to do that. Anybody have a WebAssign question? Nicole?
I have a question about one last night. I don't know if I wasn't typing it in right, but I kept getting it wrong.
Okay. Casey had a similar problem. So let's check it out and see.
The one that I didn't know was e to the negative 4x times cosine of 3x.
E to the negative 4x?
Right. Times cosine 3x.
Of 3x?
Mm-hmm. And I did the multiplication for 3, and I looked up again how to do the derivative of e to the 4x, and no matter how I typed it in, it still wasn't.
Okay. This is, we've looked at this like derivative of e to the x, so I'm going to off to the side kind of write down what we have done. And this is a little bit new, so we know that the derivative of e to the x with respect to x is what?
E to the
E to the x. So we don't really have e to the x. We kind of have this inside function that is a function of x, but it's not just x itself. So what we're really trying to do is something like this, where u is that inner function, or in this case, the upper function. I think we've maybe done a little bit of this to this point in time, not a lot. So the derivative of e to the u is itself e to the u, and then what's the kind of the new stuff in the most recent sections of this? Good. We've got to derive u with respect to x. So there's the kind of the chain rule part of this problem. So you're right, it's the product rule. So I'll write this down. First, leave it alone, just write it down, times derivative of the second plus second times derivative of the first. Now, we haven't used the chain rule yet. We've just kind of set up the product rule, which is what gets us started in finding the derivative of these two quantities, which is a product. They both have variables in them. First, what's the derivative of the cosine of something?
Negative 3 sine. Negative.
Of that same thing, right? And
Times
then
the inside.
derivative of that thing, right? So the derivative of the kind of the inside variable, derivative of 3x is 3. Is everybody okay with where that 3 is coming from, why it's necessary? That's the chain rule on the fact that we don't have just the cosine of x, we have the cosine of 3x. So that's first times derivative of second. All of this is derivative of second. Second times derivative of first, derivative of e to the negative 4x, okay, is e to the negative 4x times the derivative of negative 4x, which is negative 4. Now, did that catch your error, or are you okay so far?
That's exactly what I got.
Okay.
Did you type it in your XP?
Yeah.
Mhm.
All right, let's keep going, see if we can figure out what might be going on here. Do we have any numerical? So of this term,
You have to put the 3.
in this term, is there any kind of monomial numerical coefficient that we can pull out front?
E to the negative 4x.
Yeah, you-
Not 3 and negative 4, so nothing numerical, right? So, and then we look at e to the negative 4x. It's present in both of them. Anything else that's present in both of them?
Negative 1.
Negative 1, so let's bring that out. Negative e to the negative 4x. And I think everything else has to stay. So we've got 3 sine. Remember to put your parentheses here, right? Right?
Yes.
All right.
3 sine 3x plus 4 cosine 3x. Everybody in agreement on the answer? Now let's think about coding kind of WebAssign type issues. E to the negative 4x is exp, parenthesis, negative 4x. So that might be an issue. Sine, you do need to use parentheses around the 3x. And if it's still not liking it, I kind of keep going with different iterations. I'll come down to 3 star sine 3x, and then it has to pick that up as multiplication. And I could do the same thing, negative 1 star exp negative 4x. It might actually be a browser-specific problem that you're in Netscape, and it's symbolically it's not doing what you had done the day before in Safari or Firefox. So if you think you're doing things right, just switch your browser to another browser and try it again with the same entry. Anybody see any other help? Any kind of Chandler? Any?
Well, instead of she didn't. We were talking about this. I got it right, but what she did was instead of combining the negative 4 prior, like the boxed section. That
Yes.
Instead of combining that negative 4 with e to the negative 4, no, all the way up before you did
up
all
here.
that. Yep.
Okay.
Combining that negative 4 to e to the negative 4, instead of combining that and then putting the 3 in front of the negative sine 3x.
Okay.
And she, instead of doing all of that, she got it wrong, so.
I kept them at the end. I didn't
Okay.
put them in front. So
Yeah, I would bring them
I
in
did
front.
too, though.
It shouldn't matter, but it might be interpreting that you have sine of 3x times 3, so you really have kind of the sine of 9x.
Right.
I would always put coefficients like that out in front,
Okay.
and it's going to like it a lot better. Visually, I like it better too, because it's not confusing to me. If I see sine of 3x times 3, I'm not 100% sure what that means. Is that 3 sine 3x, or is it sine of 9x? I just think it's better to farm those things out in front. All right, any other homework question or problem, Chandler?
I'm still working on the implicit stuff for the next section. Number 3.
Okay, is it logs or?
No, it's
Okay.
well, it's got e to the x in it, so
Okay,
yeah.
but not logs or natural
No.
logs. All right, tell me what it is.
Okay, the question is y to the 5th plus x squared y to the 3rd equals 1 plus y e to the x squared.
Is that it? That's too hard. Let's not do that one. Let's just go on to some easier stuff.
That's
It's-
just long.
Sounds
It's
good.
long.
Oh, I'm kidding. Obviously, no. I mean,
like,
it's a You're looking at me like, oh no. What kind of teacher do I have here? Y to the fifth. All right, so everybody agree? Implicit differentiation.
Yeah.
I mean, if you don't agree, do you know what you're agreeing to? You're agreeing to solving this for y. In terms of x,
Which you can't.
I certainly don't want to go there, and I know you don't want to go there. So let's differentiate implicitly. Derivative of y to the fifth.
5y to the fourth dy dx.
Okay. What do you see right here?
Multiplication.
Product. So we have to use the product rule. You know, there's a lot of errors made, and I don't know why, because I know when people look at that, they have to think of a product, and I think they're trying to work too fast, and they find the derivative of x squared, and they multiply it by the derivative of y cubed, and they move on. But when it's a product, you have to use, we have a special accommodation for that. You have to use the product rule. First, what's the derivative of the second?
3y squared dy dx.
Good. Plus second times derivative of first.
2x.
Okay, and when I say derivative of the first and derivative of the second, we're deriving with respect to x, because we want our final answer to be derivative of y with respect to x. So that's that side. Derivative of 1,
0.
0. Over here we've got another product.
Oh, that's where it messed up.
First times derivative of second. What's derivative of e to the x squared?
E to the x squared times 2x.
Times 2x. Good. And that then we need second times derivative of first.
1 times e to the x squared.
E to the x squared. Oh, do you have to put dy
Second.
dx right there?
Well, aren't you deriving y
Yeah.
with respect to x? If you ask yourself the question correctly, it answers itself.
Okay.
So here's the question you ask yourself. So I'm in the second part of this. Here's where I am. I'm in the second part of this product rule. So it's second, boom, times derivative of first. Well, what is the first? I'm deriving y with respect to x. Does that answer itself?
Yep.
Listen to the question. What's the derivative of y with respect to x? Oh, it's the derivative of y with respect to x. So it answers itself. Now, this was a question, and if your question has been answered and we're okay, then we can either move on to another problem or go on into... everybody okay with how to take this from this point and solve it? No? We
No,
need to go
because
further?
I did that, and
Okay.
it's put
Let's
it
go
in
further.
Okay.
This is plus, so we've got this term and this term and this term, so 3 separate things being added. This is plus, so we've got 0, just forget about that. We've got 2 things being added over here. What is the task?
Get dy dx on one
Okay,
side.
isolate dy over dx. So 5y to the fourth, or I guess the terms that have dy over dx in them. There's a 3x squared y squared. This one we're going to send to the other side. And then this one is on the other side. We need to bring it over to where we are now, which is minus. This term is on the other side. We'll leave it alone. And this term was on the left side. We're moving it to the right side, so it's now negative. Check me now as we go, because I don't want to lose terms, and I don't want to have a positive term that really is negative.
Yeah, that's right.
We okay?
Yeah.
What's the goal then? Why did we put all the dy over dx terms together?
So you can pull it out.
Okay. 5y to the fourth, 3x squared y squared. And last step algebraically is to divide by this stuff that's in brackets that's being multiplied by.
Maybe I put it in wrong because I got exactly
Okay.
that.
So that's gone, that's gone. dy over dx is this quotient, right? Kind of an ugly answer, but I don't think anything in going from the start of this problem to the bottom of this sheet of paper, I don't think anything's unfair. That I would consider this to be a fair test question.
I think it's just a lot of web assignments and taking.
Yeah.
Yeah.
It's a little finicky. It's
You
probably
add
not
too
as finicky
many
actually as
things.
Maple, but sometimes you do have to kind of guard how you're entering things in.
Just making sure I did it right too.
Anything else from WebAssign that is pending? Yes, Blair.
Do we not have Maple this week?
No.
Do not. No.
Okay.
I'll try to announce it on Monday or Tuesday when we do. The next time we have Maple, and this is for this group of students in class right now. Maple 3 begins on the 13th of October. So, got a ways yet. Any other questions before we advance to 3.7? This is the last section prior to your test, the students that are in this classroom right now.
Really?
So we'll have some time, I hope good time, to kind of take each thing that the test is going to cover, and if it's not kind of locked in there yet, we'll hopefully lock it in before your test on Monday. I think I'll switch, Leonard. So I don't know. I played basketball last night. I don't know if I can stand. Kind of had a hard time getting over here today.
No. Why not? No. Yeah, not at all.
All right, 3.7, derivatives of logarithmic functions.
Yes. Sweet.
So we want, we're going to have a function. It's going to look something like this. Log to the base a of x. And we're going to put in different numbers for a. And we're also going to put in e. E is a number that's going to go in that position. We don't normally call that log to the base e. When e occupies that position, what do we call that? That's called a natural log. So this is going to be basically for all logs, whether they're natural logs or not natural logs. I think we would all agree that we don't have the ability at this point in time to do this problem. But sometimes if we rewrite it into another form, then we do, in fact, have the ability to do that. The base in this statement is a. What is the exponent in this statement?
Why?
Y is the exponent because a logarithm is an exponent. So y is the log. So that says y is the exponent. So the base is a. The exponent is y. And then there's really only one thing left. If we were to take a to the y power, according to this statement right here, what is a to the y power? It's x. So these say the same thing. One's an exponential statement, one's a logarithmic statement, but they say exactly the same thing. So if we want to know from this first statement what is y prime, then we can really just derive the second statement and we'll get the same answer because they're 100% equivalent. So what is the derivative of a to the y?
A to the y times the natural log of
A to the y, and we haven't used this one for a while. The derivative of a to the y is a to the y natural log of a, and then there's some more because the exponent is y. We've got to take, since the exponent is y, derivative of y with respect to x. So you might need to kind of go back in your notes, and when we did 2 to the x and 3 to the x, we got derivatives. Let me just, when we had y equals 2 to the x, we found earlier in this course that the derivative of 2 to the x was itself 2 to the x. Why? Because we ended up having that in both terms, and we factored it out in front. And then the rest of this baggage became the natural log of 2. So we've encountered that before. So we've got a to the y. Let me get rid of that, actually. See if I can get rid of that. We need to solve, I'm sorry. That's the derivative of the left side. Derivative of a to the y is a to the y, natural log of a, dy over dx, because the exponent is y. Derivative of the right side is 1. So we need to solve for dy over dx. We've been doing enough of this lately.
You just divide
Divide both sides by
the y.
a to the y and natural log of x. So if we divide both sides by a to the y and natural log of a, we end up with that. And if some of you I know have done some calculus before this course, that's not the final answer. We need to get rid of a to the y, and I think we can do that if we'll just backtrack here. What is a to the y equal to? It's x. So where we see in our answer an a to the y, whoa. We will replace that with x. A to the y from our original exponential statement, which came from our original logarithmic statement, a to the y is equal to x. So remember what we started with. We started with what? We started with y equals
Log base a of x.
and when you start with that statement, its derivative is 1 over x natural log of x. So if you haven't encountered that before, jot that down. Even if you have, and it's been a while since you've dealt with that topic, jot that down. So if we have a problem like y equals log to the base 3 of x, this is a pretty simple problem. And we want the slope of the tangent line basically anywhere in terms of x on this curve. It ought to be 1 over
X times the natural log of 3.
I'm going to draw a picture when we get to natural logarithms that I hope kind of validates that this slope is 1 over x. Natural log 3 is kind of an ugly number. Let's wait till that gets a little simpler before we look at a picture. In fact, let's do that now. Let's get one that's a little worse than this first. Let's suppose that y is equal to log to the base 5 of 2x plus 3. So we don't just have a function of x, a log of x, we have a log of something else. So tell me what to write down to fulfill all kind of pieces of the chain rule and everything else.
1 over 2x plus 3 times 2 times the natural log of 5.
Now, is that kind of the rule? And I know you said something else I haven't written down yet, but I'm going to say that. Is that the kind of the basic rule? That what was occupying this position comes down here, right? The natural log of this number goes right here. Now, that's if it's just x. But it's not just x. It's 2x plus 3. So what do we always do last when it's not just x, but in this case it's 2x plus 3?
Do the derivative of the
Derivative of 2x plus 3 with respect to x, which is a 2. Now, where's the final resting place of that 2? Numerator or denominator?
denominator.
That's in the numerator.
Why?
Because it's times derivative of 2x plus 3 with respect to x. So it's this fraction times derivative of 2x plus 3 with respect to x. So the final resting place of that 2 is actually in the numerator. All right, let's suppose that instead of having base 2 or base 5 logarithm, we have a base e logarithm. Log to the base e. And we all said that is not what we normally use. We normally call that natural log.
Yes.
So this is the same thing as y equals natural log of x. Derivative, I mean, it's a number. It's just a number that we know exactly what it is, same as we would have 2 or 3 or 5 in that position. So y prime, if it is a logarithm, it ought to go like 1 over x natural log of e.
It goes
It's
away.
1.
And that goes away because it's 1, right? Natural log of e, that's the power you would raise e to get e. What power do you raise e to get e? That would be 1, right? So that's 1. So if you have a natural logarithmic statement, the answer even gets simpler than kind of a general base logarithmic statement. So it's just 1 over x.
Is that just like the derivative of x over x?
Is that,
Like if you had log base e of 2x, would it be 2 over 2x?
okay, that's a good problem. Let's do that one next. So you have y equals natural log of 2x?
Yeah.
Because this is an interesting phenomenon. I think we can kind of rewrite that problem and validate that the answer is in fact what it is. It should be 1 over 2x times what goes in there?
2.
Derivative of 2x, which is 2. And that 2 then resides in the numerator. So you end up with 2 over 2x, which is really just what?
1 over x.
1 over x. Now, why was that derivative? Derivative of the natural log of 2x. Why is that exactly the same as the derivative of natural log of x? That seems a little bizarre.
I don't know, but
Because the chain rule cancels it out.
Okay? But let's go back to the original problem. The original problem is natural log of 2x. Let's rewrite that.
Is it just because you're changing the number in front of the angle?
Well, it's not an angle. It's
Well-
just a value that you double x before you take the natural log of it. Isn't this the natural log of a product? How can you rewrite the natural log of a product?
The logs added together.
Added together, right? The sum of the logs. Isn't this the same as natural log of 2 plus the natural log of x, right? That's not calculus. I mean, that we haven't done any calculus yet on that problem. So if it doesn't seem right that they have the same answer, what's the derivative of the natural log of 2? What is the natural log of 2? It's a number. What's the derivative of a number?
0.
Is 0.
Yeah.
That's a number. Derivative of a number is 0. What's the derivative of natural log of x? 1 over x. That's why they have the same answer.
Okay.
Because you could rewrite it, kind of split it out into the natural log, or excuse me, the sum of 2 natural logs. The first one is a number. The second one is the variable. All right, you know they're going to get worse, and you know we have to have our dose of trig today. So let's say we don't have the natural log of x, we have the natural log of the sine of x. So this is our so-called inside function, right? First thing you do is take the sine of x, and then after you take the sine of x, the next thing you do is take the natural log of that result. So somebody tell me what to write down. Natural log of sine of x, what is its derivative?
1 over sine x.
1 over sine of x. And what goes here?
Negative cosine of x.
We all right?
Yeah.
What's derivative of sine of x?
Negative cosine of x.
It is?
Cosine.
Cosine. So what's y prime? Cosine over sine? Cotangent?
That's the answer.
Everybody see where that cosine is coming from in the bracket? So it's a chain rule. It's because we don't just have x in this position, we have a function of x. So the last thing you have to do is derive that. Let me finish with this. We've got a minute. I think I can do this in a minute. Let's get a real quick picture so that we think that the derivative of natural log, which is 1 over x, we think that makes sense. So a natural log looks like this. The fact that it gets flatter, everybody agrees that it gets flatter as you go out? The derivative should be getting closer and closer and closer to 0, right, if it's getting flatter and flatter? So at, let's say, 1, the derivative should be 1 over 1. Does that look like it's kind of close? Derivative is 1 right there? Let's go out to another value. Let's say at 4, what should the slope of the tangent line be right here? It ought to be 1 over the x value, which is 1/4.
Yeah.
Let's go out here to 10. What should the derivative be out here?
1/10.
It ought to be 1/10. Does that look like that's happening to you? Slope here is 1. The slope here is 4. Keep going out to the right. If we go out to 1,000, what's the slope of the tangent line at x equals 1,000? 1 over 1,000. So it seems like it might be legitimate. I will see you tomorrow.